Now let us consider the equilibrium equation for a rigid body under a coplanar force system. From the equilibrium conditions, three equations follow. The sum of projections of all forces on the axis x is equal to 0. The second equation is that the sum of projections of all forces on the axis y is equal to 0. And the third equation, the sum of algebraic moments of all forces with respect to an arbitrary center is equal to 0. With these three equations, we can solve problems in practice, calculating unknown reactions of constraints or geometrical parameters of a model. In particular, considering the equation of a jib crane, we then have an FBD of the structure and can deal with a coplanar force system. In this case, choosing the point A as the center of reduction and the axes x and y, we can write down the equilibrium equations for the jib crane as a sum of projections of all forces on the axis x, the sum of projections of all forces on the axis y, and the sum of moments with respect to the point A. Along with the basic notation of the equilibrium equation, for a rigid body under the action of coplanar force system, we consider equivalent notations. In other words, three equations representing projections of all forces on the axis x and moments of all forces with respect to 2 points. It is necessary that a condition be met such that the line between the points A and B shall not be perpendicular to the chosen axis. This notation is convenient for analyzing a bridge design, where the left part is supported with a fixed support and the right part is supported with a movable support. In this case, the points A and B are handed to be chosen among the support points, and the x-axis is chosen horizontally arranged. Another equivalent notation can be used for writing down three equilibrium equations for a rigid body under the action of a coplanar force system, as a moment equation with respect to 3 points. It is necessary that these 3 points were not collinear in order to have independent equations. In particular, considering a segment of a monkey, we have a coplanar force system and the non-collinear points A, B, and C. In this case, we have analyzed the equilibrium of a mechanism link. To analyze the structure as a whole or to consider its other parts, we suggest the following algorithm. Considering the ladder design, we have analyzed the equilibrium of the entire ladder structure, or just of the left or the right part of it. To this end, we have to introduce the reactions of the internal constraints. When fragmenting the structure into parts, using the axiom of equality between the action and the corresponding reaction, by identifying the reactions of internal constraints, we shall have equilibrium of the left and right parts of the ladder in the form of three equilibrium equations. As a result, writing down three equations for the left part and three equations for the right part, we have 6 equality equations to determine the reactions of external and internal constraints.